In this problem, we're using Ampere's law to compute the magnetic field inside and outside a thick cylindrical wire of radius big R, carrying a total current of I. And at the end of the problem, we'll make a plot of the magnetic field magnitude B as a function of distance from the symmetry axis of the wire. Now we're told for this wire that we can assume a uniform current density within the thick wire. And this is a bit of foreshadowing because I'm also going to post a couple videos where current density is non-uniform. And I'll post links to those at the top and in the description when they're done. So we have a picture of our thick wire with a total current of I flowing in it, and we should put the current density in the picture as well. And we have a few things to say about this current density J before we get started with Ampere's law. So the current density is defined as current per unit cross-sectional area. So in this case, J is simply I divided by A, where A is the cross-sectional area of the wire. And we want to do a couple things with this expression. First, we can just turn it around and say the current through any given cross-section is given by the current density multiplied by that cross-sectional area. And we're going to have to use that idea when we find the magnetic field within this cylinder. Second, we can find a quick expression for the current density in this wire by simply taking the total known current I and dividing by the cross-sectional area of the wire, which is pi times big R squared. So both of these relationships are going to be useful to us later on in the problem. So now we're ready to get started with Ampere's law inside the wire. So there's Ampere's law telling us that the path integral of B dotted into dl on a closed loop is equal to mu naught times the enclosed current passing through a surface defined by that loop. And I'll post a link at the top to where Ampere's law was first derived. But to make Ampere's law useful, we need a special loop called an Amperian loop, along which the path integral is trivial to compute, meaning B is parallel to the path increments dl, and the magnitude of B is constant along the path. And this is where we rely on the symmetry of the problem and our prior knowledge of the right-hand rule for the direction of magnetic field generated by a current. So our current points to the right, and if we put the thumb of our right hand in that direction, then our fingers curl in the direction of magnetic field. To make it absolutely clear what the direction is here, the magnetic field is coming out of the page above the symmetry axis and going into the page below the symmetry axis, but we're viewing it in perspective. We also expect by symmetry that the magnitude of this magnetic field is constant as long as we use a path that shares the same symmetry axis as the cylinder. In other words, as long as the path is a circle with the symmetry axis passing through its center. Now that path is our Amperian loop for the path integral, and we've given that a variable radius little r, where little r is less than big R. In other words, the Amperian loop is completely contained inside the thick cylinder. Now we can label a particular spot on the loop to show the vector magnetic field and the path increment dl like this. So again, to clarify a picture shown in perspective, that little b vector is tangential to the Amperian loop, and so is the little dl path increment along the loop. And we're integrating in the natural direction given by the right-hand rule here, which means the dot product will yield positive values. So this Amperian loop has everything we want in an Amperian loop. B is always parallel to dl, making the dot product trivial, and the magnitude of B is constant, and now we can exploit the power of Ampere's law. So we're going to start by working with the left-hand side of Ampere's law, in other words, this path integral of B dotted into dl. Given that B is always parallel to dl, that dot product is trivial, and it reduces to the product of the magnitudes of those two vectors. So I'll just write LHS for left-hand side, and that reduces to the path integral of B times dl, where that's the product of magnitudes of those two vectors. Now we use the fact that by symmetry, the magnitude of the magnetic field is constant along this entire Amperian loop. And a constant can be factored out of an integral, so we can bring the B out in front, and we end up with B times the path integral of dl. Well, the path integral of dl just says add up all the length increments around this entire circle. In other words, that's just the circumference of the circle. And I end up with the left-hand side reducing to this, just B times 2 pi r. And that's always the essence of the trick with Ampere's law. We want to pick an Amperian loop that has so much symmetry that this intimidating looking path integral reduces to something trivial. Now the right-hand side is actually the tricky side. On the right-hand side, I have mu naught times I enclosed. But our Amperian loop has a radius less than the radius of the entire wire, so it's not going to enclose the entire current I. It's got to be less than that. And this is where we get back to the idea of current density. The enclosed current is going to be given by the current density J multiplied by the cross-sectional area of the Amperian loop itself. And the current density J is given by this expression, I over pi times big R squared. So on our right-hand side then, we have mu naught times the current density, which is the total current in the wire, divided by pi times big R squared, multiplied by the cross-sectional area of our Amperian loop, which is pi times little r squared. Our pi's are going to cancel here, and we end up with mu naught I times little r squared divided by big R squared. So now we can put everything together here and set the left-hand side equal to the right-hand side. So the path integral on the left reduced to b times the quantity 2 pi r, where that's little r. And on the right, we have mu naught I times little r squared over big R squared. One of those little r's is going to cancel, and we find that the magnetic field within the cylindrical wire itself, and we're going to call that Bn, is equal to mu naught I times little r divided by 2 pi times big R squared. So note that this magnetic field is growing linearly with the distance from the symmetry axis. I have proportionality to little r in this expression. So the farther we get from the center, the bigger the magnetic field gets, as long as we're still inside the material in the wire itself. Now to find the magnetic field outside the wire, we just draw a bigger Amperian loop. It's still going to be centered on the same symmetry axis as the cylindrical wire itself. And we do all the same stuff. We can visualize a little path increment along that loop, dl, sort of coming out of the page at us. And the magnetic field is tangential to that Amperian loop, so parallel to dl. And all the same things happen on the left side of Ampere's law. So I'm not going to show it in as much detail this time. The dot product is trivial because the two vectors are parallel, and the magnitude of B is constant by symmetry. And I can factor the B out, and the left-hand side reduces to this, just B times 2 pi little r once again. And this time the right-hand side is super easy because the enclosed current is just the entire current flowing through the wire, which is capital I. So we quickly find this time that B out, so the magnetic field outside of this cylindrical wire, is mu naught I over 2 pi little r. So this is the same result we already found for a thin wire in the previous video, and I'll post a link to that derivation at the top. So now we have expressions for the magnetic field magnitude inside and outside the thick wire. And it's time to make a plot of the field magnitude starting from r equals 0 at the center of the wire and extending to large values of r. So in this plot, we expect to see linear growth of the magnetic field starting from r equals 0, because that Bn expression is proportional to little r. And then outside the wire, we should see the field dropping off like 1 over r, asymptotic to 0 as r becomes large. But one thing I want to confirm before I make this sketch is that the magnetic field is actually continuous at the surface of the wire. In other words, when little r is equal to big R. So we can quickly evaluate Bn at big R. In other words, replace the little r with a big R. And when we do that, one of the big r's cancels, and I end up with a mu naught I over 2 pi big R. If we do the same thing for B out, so the magnetic field outside the wire, evaluate it when little r is equal to big R, and we end up with exactly the same expression. It's going to be mu naught I over 2 pi big R. So we expect in our graph that we have linear growth followed by this 1 over r asymptotic behavior, and the magnetic field is continuous at the interface. So there's the plot of magnetic field as a function of little r, where r goes all the way from the symmetry axis of our thick cylindrical wire and then off to infinity. Right at the kink is where we have the transition from the linear behavior to the 1 over r behavior. And of course that occurs when little r is equal to big R, the radius of the wire. In the next video, we calculate the magnetic field inside and outside another thick cylindrical wire, but this time we're actually going to use a variable current density within the wire. So we're going to use a linearly increasing current density, and this actually makes it necessary to compute an additional non-trivial integral in the solution. I'll post a link to that video at the upper left when it's done, and you can link to my entire Ampere's Law playlist at the lower left. Thanks for watching.